my thingy and it fell down. It is the 9th today. All right, let's get started.
Birthday, guys.
Happy birthday.
Is this? Yeah.
Today
you guys gonna do anything?
is the 9th.
Whose birthday? I don't know.
All right, so let's talk about Hess's law. So that way you guys can see the application. So if you guys remember last week, we talked about how, let me actually find the last week's notes.
Enthalpy.
We talked about enthalpy and we talked about equations. Yeah?
Enthalpy of combustion.
Yeah, enthalpy of fusion, enthalpy of combustion. So let me just point that out to you guys. So just as a reminder, enthalpy of formation is when we make a compound, we set it to 1 mole, and then we make it based off of the elements that make that compound. This has to be set to 1 mole. Everything's in reference to that. So that's one equation. The other equation we talked about was combustion, which is when you take a substance and you burn it in oxygen, and what has to be set to 1 mole is whatever you're burning. So that is the equations we talked about, and it's important that we talk about those equations because Hess's law is going to be looking at manipulating those equations to then figure out enthalpy of an unknown. So there's lots of different ways we can manipulate equations. I think the best way for me to show this to you is to actually do a practice question so you guys can see the calculation. So let me give you a rundown of what it looks like. So let me write down the equation. So with Hess's law, what's going to happen is they're going to give you some equations, and they'll give you the enthalpy value for those equations. And then you're going to manipulate those equations to figure out an unknown. So we're going to do an example. We're going to calculate the enthalpy of the formation of the zinc sulfide. So this is what we're looking at, zinc sulfide. The equation for that is going to be zinc plus sulfur makes zinc sulfide, and our delta H is our unknown. It's our question mark. S-U-L-F-I-D-E. Sulfide. Sorry, sulfide. I can say sulfate. So that's the equation that we're trying to solve for. What they do is they give you a list of equations, and we're going to manipulate those equations to figure out the unknown. So in this case, they have given me information on the formation of zinc oxide. They've also given me information on the formation of sulfur dioxide, and they've also given me information on the combustion of zinc sulfide. So I'm going to write down all those equations and the enthalpy that they've given me. So that is my unknown and what I'm trying to solve for. And my known values are following. So we have zinc, 1/2 oxygen, and we have zinc oxide being formed. And they tell me that the delta H value for this equation is negative 348 kilojoules per mole. So that's my first equation. I'm going to put in my states because it's a good idea to do that, because every so often they throw in a curveball and you got to factor in state change as well. And I'll try to find you some examples of that when we look at the no brain too small. So these are all solids. So that there is my, well, we can look at it two ways. It's either the formation of zinc oxide or it's the combustion of zinc. Both of those would be correct ways to describe that equation. They've given me should I do the equations in different colors? That way we can keep track of which one's doing what. They've given me the combustion of zinc sulfide. And that makes my zinc oxide and my sulfur dioxide. It's a gas. And that delta H value is negative 441 kilojoules per mole. So they're giving me that as my second equation. And for my third equation, they have given me the combustion of sulfur, or you can say the formation of sulfur dioxide, are both correct terminologies. Cool. All right, so those are my three equations. So what I'm going to do is I'm going to manipulate these three equations to figure out my unknown equation, and that's what Hess's law is determining. Are we okay with that so far? Okay. I'll just say this because you don't need to ever explain Hess's law, but when we're talking about the law of thermodynamics, the energy in the system is always going to be conserved. We can't create or destroy energy, just like we can't create or destroy matter. So with that in mind, Hess's law looks at different ways that we can get to the same endpoint. So with each chemical reaction, they're an independent root. What this means is that we can manipulate equations that we have to figure out a root that we don't have. So that's what we're going to look at that. With the manipulation of the equations, there's lots of different things we can do. We can flip the equation around. We can also multiply the equation as well. And those are acceptable things to do. With this, what we want to do is basically cancel things out so that way these three equations, when we put them together, result in this equation at the top. So there's multiple different ways you can do that, and there's lots of different methods in how you start it off. My personal thing that I like to do is I like to find something that's unique with this top equation here. So that way I then have a starting equation and then everything else kind of falls into place with that. So what I notice, for example, is this equation has zinc. I see zinc here. So I see zinc here, I see zinc here. In this case, then I see sulfur here, I see sulfur coming up here, I also see sulfur coming up here. And then the last one I see is zinc sulfide, which I see here. I can also see that I have zinc oxide multiple times. I can also see that I have sulfur dioxide multiple times. So there's no right or wrong way to start with, but personally, I would start with the zinc sulfide, because that to me is a unique thing. I can see in a lot of these equations that there's zinc oxide multiple times, so I don't want to start with something like that because then I have multiple manipulations to do. So first thing I'm looking for when I'm manipulating these equations is I want whatever I'm doing to match what's up at the top. So I notice that my zinc sulfide is on the reactant side, but in the equation that I'm trying to solve for, it's on the product side. So what that tells me is that I need to flip this equation. So basically, I'm reversing it. When I do that, you're going to then change the sign. So whenever I flip equations, I just change the sign. So if something's negative, it becomes positive. If something's positive, it becomes negative. Because the reverse of it is just going to take either, like if the forward is exothermic and releases energy, then if I reverse that reaction, I need to put that energy back in there. Yeah. So that's going to get flipped, and that's going to now become positive. So let's write out what that's going to look like. So if I was to flip that equation, and I like to line things up so that way it's easy for me to cancel later. So putting the arrow nice in the middle, I would have zinc oxide going first. Oops, that shouldn't be a 2. That should be solid. And I would have sulfur dioxide going next. That's a gas. And I have zinc sulfide as my solid, and my 1.5 oxygens as my gas. So that's the first thing that I've done with my manipulation, is that I flip the equation around. What I like to do then is keep a running total of my numbers to see how my numbers are behaving. So I'm going to do that on the next page because I'm going to basically add all my values together. So if I flip that equation around, what I have from that equation is going to be a positive 441 kilojoules per mole now. Are you okay with that? Cool. All right. So I've taken care of the zinc sulfide. Now what I want to do is I'm going to look at the other components in there, such as the sulfur dioxide and the zinc oxide, because I know in my final equation I need to get rid of these things. So it doesn't really matter which one we start off with. I'm going to start off with the sulfur dioxide because that's over here. So I'm checking this guy and this guy. What I'm also looking for is I want to make sure they cancel out because I don't want that in my final equation. So I see sulfur dioxide's on the reactant side. I see that it's on the product side. So that's good. I don't have to flip the equation around to get rid of it. The other thing I'm going to check is how does this fit into the main equation? So I see that there's zinc here and there's zinc there. So looking at that equation, I don't need to flip it because everything's on the right side for it to cancel out. And I don't need to multiply any of it because I know that this is matching with that number-wise, and that's going to match with that. So I'm going to write down that equation as is. There's no changes. So we have zinc, which is my solid. We have half oxygen, which is my gas. And then the product is my zinc oxide, which is my solid. So no manipulation, I can just copy that number down and to my main number tracking. So that way I know how I'm keeping track of everything. So I then have a negative 348 kilojoules per mole. So that is that equation taken care of. You should probably be using all the equations that they provide. So I've used that equation. I've also identified where the zinc's coming from in my main equation. Are we good so far? All right. Last one I'm looking at is this equation over here. And again, we're looking to see what has been given and what am I trying to get rid of. So when I'm looking at this equation over here, I can see that there's sulfur on my reactant side, and I see that there's sulfur on my reactant side in my main equation. So the good news is there's no manipulation with the flipping. If I want to double check that, the other thing I'm looking for is I have sulfur dioxide here. And I want to get rid of it because it's not, again, in my main equation. I can see that in this equation, sulfur dioxide is on the product side, so I know it's going to cancel if I line it up. So this one tells me I don't need to flip it. The other thing I need to check is, do I need to multiply it by anything? This has a 1 as its coefficient. That also has a 1, so there's no multiplication that needs to happen. If I do any multiplication, remember you're multiplying the whole equation. And you're also multiplying the enthalpy. So if I need to multiply this by 3, that's going to become a 3, that's going to become a 3, that's going to become a 3, and this is going to be times 3. Okay? So we can leave that equation as is. It's a nice, easy problem for us to do. I'm putting all those things in there. And yeah. And then I'm copying down this number and how I've manipulated it. So in this case, no multiplication, no flipping, so I can just use the number as is. I want to first double check that I have manipulated my equations correctly. There's a lot of little fail-safes you can do for this, which is good. And the good news about this question is that it's a very easy excellence if you can do your math. So let's double check that I have manipulated things correctly. First thing I am checking is, does my sulfur dioxide cancel out? Yep, because that's a 1 and it's on my reactant side, 1 on my product side, so those two cancel out. Other thing I'm checking is my zinc oxide canceling out? And I see that there's 1 on that side, there's 1 on that side, so that's canceling out, that's good. And in my final equation, I should only have zinc and sulfur, so I want to make sure the oxygen cancels out now. So I have 1.5, and I have 1.5 on that side. So cancel, cancel, cancel. So when I put my equation together, I should have what I have at the top. So zinc as a solid plus sulfur as a solid makes zinc sulfide a solid. So that is ticked. I've done my manipulation for Hess's law correctly. It's very therapeutic. It's kind of like the redox equations. You just follow the steps and it works out. So that has been done correctly. So when I go to do my calculations, I can add all these numbers together. So I have 441 minus 348 minus 297. So it's negative 204. So the delta H value is negative 204 kilojoules per mole. The good news is that this is usually a very easy excellence point, because if you can calculate that, then you're done. Yeah, easy E point there, if you're good at math. If you're not good at math, then I'm sorry. But if you practice it, then it's an easy excellence point. You just got to learn how to do it. Some things that will mark you down to merit would be if you got the sign wrong, if you forgot 3 significant figures, that's a common problem, and if you forgot your units. So any of those things can mark you from an excellence to a merit. It's a lot of work for the merit between the achieve and the achieve and the merit, but the merit to excellence isn't too bad. I can't quite remember what the achieved criteria is. It's normally that you've done it mostly right and you make a silly mistake. So silly mistakes tends to knock you down to achieve. Say, for example, you manipulated the equation the wrong way. And that's all you're looking at for Hess's law. Do you guys feel like you need another example? Kind of?
Yeah.
All right, let's look at no brain too small. I'll pull up a question from there.
And you wanted to show us like what it looks like on the exam.
Yeah, I can pull that up too. I was gonna just look it up so that way I didn't have to keep flicking back and forth between screens, but if you want, I can show you what those calculations look like. I like I said, the no brain too small because it collates the questions. So that way we can actually see different ways they ask the same one. And we want the collated questions for the enthalpy. Now be mindful that this is going to have both Hess's law and the other calculation. We'll do the other calculation later. But this one from 2021, you can see what I'm saying about the manipulation of the equation. They give you a list and then you have to manipulate them. And they often love this question here. Explain why the standard enthalpy change calculated in part 1 would be more exothermic if the water was produced as a liquid. So in this case, we can see that the water is being produced as a gas. That's a common follow-up question because then you have to just talk about how the energy is being used. Well, in this case, you'll save energy because you're not having to break all the bonds to make it from a liquid to a gas. So they ask it in both ways. And that's what I'm saying, that you have to pay attention to state. Would you like me to do this question so you can see another example? Yeah? Okay. Cool. I'll copy that down to my sheet. So you can see another calculation. So we have ammonia being combusted. So that would be 4NH3, which is a gas, plus 5 oxygens, which is also a gas, becoming nitrogen monoxide, and water, which is a gas. Cool. And they've given you the following data. So we'll write down those equations too. So they've given us the reaction for making ammonia, or breaking down ammonia actually. And the delta H for that one is positive 92. The second equation is the Degradation of water. Or decomposition of water. That's the word I was looking for. And as you write states, what is that? Positive 572 kilojoules per mole. We'll also look up the marking schedule so you guys can see what I'm saying about how it's an easy excellence point. I really like Hess's law because, like I said, it's very therapeutic to work through. And then we have the combustion of nitrogen. I'm just copying it down onto my piece of paper, and then I'll shift it. But yeah, it doesn't really matter where you want to start. I just personally like to start with one of the products that's kind of unique looking, so that way I know it's going to cancel. All right, cool. Cool.
Is this like a frequently asked question?
Yeah, and I think actually, where is it? There's a audit. I'm trying to remember what website does it, but one of the websites, I'll have a hunt around, does an audit of all the questions they ask, so you can see what they asked what year and how frequently it comes up. I'll have a hunt around. But yeah, they're probably going to ask this. So you can see when it comes to the questions that they ask for enthalpy, they often ask the enthalpy calculation, which we'll do next week, and they ask a Hess's law question. So you can see it's there. Sometimes they give you a shorthand version of it, and I'll show you how to do those calculations. You can do it longhand, but you don't need to. But they often ask. So here's another Hess's law question. They ask it to different difficulty levels. All right, so let's do that calculation, and then I'll show you the shortcut version, which is nice. All right. So again, depends on what you want to start with and how you want to manipulate equations to figure things out. Personally, I like to start with things that are on the product side and then work my way backwards. And I'm trying to find things that like you don't see multiple times. So like the nitrogen is something I see multiple times that I know are going to cancel out. So I'm probably going to do that later. I would start with the nitrogen monoxide, this here. But really, honestly, you can start with anything. So it's up to you. Okay? So I'm looking to see where I see that in my equations, and I see it over here in my purple equation. Things that I'm checking, is it on the right side to match the equation on the top? And then is it the right multiple? So these are both on the product side, so I don't need to flip anybody, but I see that this is a 2 and that's a 4. So I'm going to have to multiply by what number? 2. So multiply by 2. You don't need to write out the whole equation and do all the canceling. If you're trying to save yourself some time, you can just go with your gut and just show that you're doing that multiplication. So if I was being lazy, I would just go, okay, so it's positive 180 times 2. So that's 360. If I was being lazy. If I want to be double checking my work and making sure I don't lose an easy excellence point, I would actually work out to make sure that things are canceling properly. So if I was to write out this equation and I multiplied it by 2, we would have 2 nitrogens, we would have 2 oxygens, and we would have 4 nitrogen monoxide. If I was doing things the longhand way. All right, we okay with that so far? Cool. The other thing you can do is you can just go through it equation by equation and see what matches and how you're going to manipulate it. So let's go through pink because it has the ammonia. So I see it's on the reactant side, and I see it's on the reactant side of my main equation, so no flipping required. I do see that's a 2 and that's a 4. So what that tells me is you need to multiply this by 2. Again, if you're lazy and you don't want to write out all the equation, you can just state that you're doing that. Then you do 92 times 2, which is 184. But if you want to show you're working, and it's useful to show you're working because then the examiner knows where your mistake is. So I would write down, this is 4 and H3, and there's nothing to plus there. And then that's 2 and 2, and that would be 6 H2. And you can see stuff is already going to start canceling out. All right, last equation that I'm going to manipulate is this guy over here. This one, now I look at the original equation. There's no hydrogen, there's no oxygen, but I can use the water as my reference point of how I'm manipulating things. Because I see there's water on this side and water on that side. So I'm looking at this guy, I'm looking at this guy. Now I see on my main equation that it's on my product side, and on my given equations on my reactant side. So that tells me I got to flip it. So I'm going to make a note that this needs to get flipped. The other thing is I check the coefficient in front. That's a 2 and that's a 6. So what should I be multiplying it by? Yeah, flip and times by 3. So if I flip that, that should now be a negative 572, and I multiply it by 3. So again, if you're being lazy and you don't want to double check yourself, you can just do this math and write down what you're doing. So these are my 3 equations and how I manipulated them together. And then I can figure out my final answer there. Or you can write out the equations and double check yourself. So let's double check myself because I think that's a good idea. All right, so with that equation, with how I've manipulated it, these guys would be my reactants. So it would be 3 times 2, so 6 H2s, which is a gas. I have 3 O2, which is a gas. And on my product side, I would have 6 H2O, which is a gas. And if I want to double check to make sure everybody cancels out for my main equation, I see there's 2 nitrogens here, 2 nitrogens there. That cancels out. I see that there is, what else do I want to cancel out? Hydrogens, 6 on that side, 6 on that side. And I think that should now be the equation that I want. So my equation that I want to have 4 ammonias, which I see up here. I want 5 oxygens. 2 plus 3 is 5, so that works out. So it's a good way to idiot check yourself. Because it's not somewhere you want to lose your excellence point. All right, 4 and 4, 6 and 6. Everybody checks out fine. Like I said, very therapeutic to work through. Cool, that checks out. So now I'll go through and add my numbers. So 360 plus 184 minus 1,716, I get negative 1172. If I want to round that to 3 significant figures, we go 1, 2, 3. I'm rounding to the 7. If it's less than 5, we drop the numbers. If it's greater than 5, we round up. So in this case, I am going to drop the numbers, and I have negative 1170 kilojoules per mole is my final answer. And that's basically it. Yeah. And that's all you got to do. Not too bad, eh? And that would be your excellence point. Now let's check the NZQA to see if we did the math properly. And this is where Miss embarrasses herself because she didn't do the math properly. Yeah. These are the examination papers. Let's see, level 3. assessment schedules. We were looking at the 2021 thermo, and that was question number 2C.
Yep.
Yeah,
Yay.
Miss got it right. All right, so we can see here how things go. So for the excellence, correct answer with correct unit, sign, and significant figures, plus explanation for this part here about how if we had a reaction occur, it would be more exothermic because we are not wasting that energy breaking the bonds between the water molecules. For the merit, correct process with one error. So maybe you've dropped a sign somewhere and that's affected your answer. So my recommendation for you guys is to always show your working. If you just write down your final answer and your final answer is wrong and we don't know why it's wrong, it's going to be not achieved. Okay? So show your work. Even if you're being lazy and you're just showing this stuff here, that's enough for me to know what you did wrong. And then for the achieved, you just need to correctly manipulate one equation. So you need to flip it or you need to multiply by 3 for one of them. There are 3 of them. So that's a real basic thing you can do. So, and that gives you multiple opportunities to show that. So if I'm looking at this, this manipulation here where I multiplied it by 2, this one where I multiplied it by, I think, 2, this one I flipped and multiplied by 3, that's 4 chances to show an achieved. Okay? So take your guess. Even if you're doing your math wrong, there's lots of chances to that. All right, feel okay about that? All right, shall I show you a little bit of a shortcut?
Yeah.
All right, so there's a nice little shortcut, but with the shortcut, you could only use it if everything they give you is in the formation equations. So let me show you an example, and I'll grab some different colors. So they want you to calculate, in this example, the combustion of ethanol. All right. When it comes to calculating the combustion of ethanol, they've given you the equation that you're trying to get, C2H5OH liquid plus 3 oxygens, whoops, makes your carbon dioxide and your water. Cool? Now, you know how in the last example they've given you the equations? In this example, they don't give you the equations, they just give you the enthalpy value for the formations. So they say that the delta FH of ethanol in the liquid form equals negative 278 kilojoules per mole. They say the delta F for water, and this is in the liquid form, is negative 286 kilojoules per mole. And then the formation for CO2 in the gas form is negative 394 kilojoules per mole. All right, so I'm going to make the note that the shortcut only works if you have everything in formation. All right. If you look at the other 2 equations that we were looking at, those didn't have everybody in formation. So that was formation. That one was, actually, wait. Were they all in formation? Yeah, they were all technically formation. So you could, nope. I lied. That one's formation, that one's formation, that one was combustion. So you couldn't use the shortcut. In the example that we're looking at from the assessment, this one was obviously the other way around for a formation. Same with that one. And that one was a formation. So that's what we're looking for. In theory, you could have probably manipulated the other two equations to be all formation, but it would have probably complicated things. So the reason why I taught you guys last week about combustion and formation and how to write those equations is because you could write the long answer and figure out what these equations look like. But you can do a shortcut because all of these are in the formation version. So the way it works is that we can figure out this equation up here if we take the enthalpy values of all of the products and we subtract away all of the enthalpy values from the reactants. Some people don't like this because they would rather do the longhand and just double check themselves. So what does that mean? So what we're looking for is we are identifying if these guys here are products or reactants, and we're checking the ratio of things. So in this first equation here, I have the ethanol. Ethanol is a reactant. And the other thing I check is the coefficient in front. So this coefficient is 1. So this number here is going to go over there. So that is the negative 278. We okay with that? All right. This next one here, water. I see that it is a product. So it's going to go on this side of my equation. I see that the coefficient is 3. So I need to take this number and multiply by 3. So 286 times 3, that's going to be negative 858. Are we okay so far? All right, last number that I have to deal with is my carbon dioxide. I see that carbon dioxide is also one of my products, and I see that there's a 2 in front, so this needs to be multiplied by 2. So I'm going to also have negative 394 times 2. So that's 788, and that's negative. Are we okay with that so far? Okay. And then I just put it all together. So delta H is going to equal my sum of my products. So that's negative 858 plus negative 788. So that has negative 1646. And I'm subtracting away my reactants. Remember, you are subtracting away a negative number. So you're actually adding. So negative 1646. If you want, you can do minus and negative if you want to double, check that you don't do things wrong, but it's basically going to add it. 278. And so we get my delta H is equal to negative 1368. And if we want to do 3 significant figures, 1, 2, 3, I look at that number, it tells me to round up. So my delta H should be negative 1370 kilojoules per mole. So that's the other way you can do it. Only can do that, though, if everything they give you is in formation. If you want to do it longhand, what you can do is you can write out the formation equations for each one of these and manipulate it the same way that you do Hess's law. You should get the same answer. But if you're trying to do something quickly, that's the shortcut. But like I said, only works for some of the equations. So I'll go show you guys the no brain too small again. So we can see those questions. So this one is an example of that. You see how you have your original equation and then all the enthalpy values they've given you is in formation. So you could use that shortcut for this one here if you wanted to. And if we're looking at the marking schedule, you see how they have done the shorthand version here too. So they've just put in what's reactant, what's product, and they put in how many times you're multiplying it by. You don't need to worry about switching signs or anything because it's already built in with the way the equation's set up. So don't worry about flipping anything. Okay, but if you were to do it the longhand way and you would flip things around, it would result in the same answer. And this one here is a little bit frustrating because it only goes up to merit. So, but yeah, that's all for the enthalpy. And then we'll talk about the other enthalpy question calculation, which is a little bit more complicated. There's lots of different ways that they might ask it. I'm trying to remember what the audit is called. Let me see if I can find it.
Miss White, can you go into
Yeah.
Hess?
Do you want that one?
Yeah.
All right, I'll freeze that and I'll pause the recording and I'll try to find the audit that I was talking about. Right, I think it was this one, GZ Science. And if we go to level 3 chemistry and we go to that one, which is our thermochemistry, they have something, they have some really good stuff here. They have a sheet here that is all about focusing on the excellence and what you need to do for that. But the one I wanted to show you was the audit. Do they have that? Maybe I'm wrong. Maybe that was it. Do they not have it?
Wait. No one wants to be in your room. You're thinking that some
Workbook,
I'll be in the room.
teacher notes,
Oh,
Get out of here.
yeah. That's
walkthrough,
my guy.
checklist.
What's going on?
Maybe that is it.
I just think it was your brother. Makes it kind of gross. Yeah, to be honest.
Yeah, this is the one I was thinking about. Sorry. It's the same one that's referring to about like getting to excellence. Yeah, focus on excellence. So what this shows you is a really useful tool because it goes through all the past exam paper, well, not all of them, up to 2019 by the looks of it, and it tells you what they asked as the particular question, so what atoms did they use or what ions they used, and they also summarize if they gave an achieved merit or excellence point to it. So it's a nice way to kind of know how they distribute the points. And what they talked about, so you can see how many excellence points they gave each year. So if you guys are curious to see basically how much work should you put into a question. So we were just looking at the calculations. Do they have Hess's law? That's heat capacity. Here you go. So you can see the enthalpy of formation. You can see what they asked each year and what, if they awarded a merit or excellence point, that's the shortcut version that we talked about. And then this is the long version with Hess's law, and they say, what did they do, and this, they awarded excellence. So for 2016 and 2017, they didn't ask that question, which is really weird. But 2018, 2019, they did. Obviously, 2020 we saw, or sorry, 2021 we saw. I would assume it's in 2020 as well. This is a common question. So yeah. And they've given you also the grade boundaries, which is useful, so you know if it was at 19 or 20 points. So it's a useful tool.
Now you're supportive of understanding. Back then you weren't. What?
Yeah, so this one here, they go through a list of the formation ones, so you're probably going to get that, so it's worth practicing the shortcut. Yeah, I can put that on.
Yeah.
You can see, especially when they're doing that enthalpy calculation that we look at next week, it's useful to see what they ask, how frequently, and what it's worth, because there's lots of different ways they can ask the enthalpy calculation.
Yeah.
So it's a matter of which one you want to focus on and how they do it. And then we'll also talk about entropy next week as well. And that'll basically wrap us up for thermo. And like I said, you can see all the other stuff we covered. So the phase changes, that sort of stuff. The shapes and polarity. Basically, you know how much to invest into each style question. So I'll put that onto Google Classroom as well. But if you want to look at the whole website, this GZ Science is a good resource because it summarizes everything. And it links everything that you could use. They even have a study guide over there, so lots of stuff. Some of it's free, some of it you gotta buy. And there's lots of videos on there too. This guy's my friend.
Oh, I like that guy.
Science guy? I know him. He's a friend of mine.
I was watching it for what it was, something in chemistry. And
Yeah.
it was like really helpful.
Yeah. That's a friend of mine. He also has his golden retriever in some of the videos.
Oh, yeah, I know.
Toast.
At the end,
Oh, he's
yeah,
really
they'll
good.
show it.
Yeah, I've met Toast. Toast is a very lovely dog. Anyway, so yeah, I know him. My little claim to fame is that I know him. So yeah. Anyway, I'll link that all.
Okay.